Hello students. In today's class we'll conclude our discussion on biological networks. So in last few classes we are discussing about these beautiful complex structures that emerge out in biological systems, and we learned several different things about these network structures. We call them graphs. We also defined nodes and edges and degree hubs, right? Random and scale-free networks. So these are the terms that you should be familiar with if you had a course where biological networks have been taught, right? So these things you have learned. We also learned about the versatility of this network. So biological or otherwise, we saw that when multiple agents are involved in a particular task, they are all contributing in some all contributing and affecting each other in different ways. So then you can form these complex structures of networks between them, and you can analyze them in a broad sense, considering the heterogeneity in it, without considering the homogeneous mixing in it, right? So we saw that it can emerge out from social contact networks to gene regulation networks. We also discussed several networks otherwise other outside the regime of biological as well, right? Like the author collaboration network for scientific publications, actor collaboration network in movies, and so on, right? Flight networks between cities. So different way you can think about this structure. So how to analyze or quantitatively analyze these networks? We also defined about network matrix, right? So a network matrix where the terms or the particularly defined quantitative definitions that we had about analyzing networks, we call them network metrics, like degree distribution, assortivity, clustering coefficients. These things we have defined, right? And we also learned about matrix representation, list representation of networks. So we learned about adjacency matrix, incidence matrix, and adjacency list. Then we learned that how to represent a network in terms of matrices, because then once you have the matrix, you can handle it easily with any programming language that you know. So those people who are interested in writing codes, who are inclined, students from computer science, ECE, other disciplines who are inclined to codes, they can easily now handle these matrices and study different things from there. So these are the definitions that makes the thing much more easier. It turns a conceptual connections of like 10,000 nodes in form of a matrix, which is much more easier to handle mathematically, computationally. And finally, we discussed about network building blocks in the last class. So that was a very important thing that we discussed, and we especially focused on feed forward loops, a major contributor in control for biological networks, especially gene regulatory networks, right? So today we will learn directly about application of these things that we have learned so far in last few classes, and we will focus on the problem that we are already familiar with, that is networks in epidemiology. That is how the epidemic that we are seeing all around us, we have analyzed it with differential equations so far. Now we will see how we can analyze it using the heterogeneity on network structure. So just to quickly remind you, we have, when we wrote down those differential equations in SIR model to analyze it, we also raised that there are some limitations in this homogeneous approach. Why do we call it a homogeneous approach? For the same reason that we considered that S is a population or a compartment, I is a population or a compartment, and we do not consider that which particular person, susceptible person, is infected at a time point, right? We consider that everything is completely mixed and anyone can catch the information from anyone. So like a very tightly connected group, we consider them a very well mixed population. So deterministic approach, that is the differential approach, homogeneous approach, all are the same names for the all are the different names for the same thing. So they can answer questions like how many, right? So questions where you raise global issues, and you try to answer global issues like how many people are infected, how many will remain infected in the steady state, right? Is the state that I am seeing is stable or unstable or maybe bistable, right? Is there any bifurcation? So these kind of questions we can answer from deterministic approach. But this particular approach is completely silent on questions like who, that is the individuality, right? Who are likely to be infected? Individual nodes, which particular person is likely to be infected? Which person, who are the critical persons for infection spreading? So these questions we cannot answer. So all the population level statistics is provided by this approach, by this homogeneous deterministic differential equation based approach, but the information related to particular individuals are missing. So that is the limitation of homogeneous approach, and there comes networks. So if we have learned that networks, how they look and how the structure looks, we can understand now step by step that if I want to understand or simulate, so to say, computationally generate, computationally try to reproduce whatever is happening in the society, then how do you approach the problem? So let us just learn about it. So what we will do is, suppose I have a small network with 5 nodes where this is the connection and this is the adjacency matrix for this network. Okay, so this is the connection and this is the adjacency matrix for this particular network. Now what I consider is that suppose this one node has become infected, just like we introduced that some susceptible in a huge number of susceptible people, some small fraction have become infected to begin with. Here I consider out of these 5 nodes, one has got infection. Okay, now how will I deal with the problem? I will label these nodes in my matrix. So I will label that one is now infected and rest of them are susceptible. So one is infected and rest of them are susceptible. That is how I label it. I add an attribute or a property to these nodes computationally. This all happens inside computer codes. So I am not asking you all to dive into this and write the codes right now, but those who are interested, they can try and attempt this problem. This will be a nice exercise for you, and if you learn this, trust me, there is a huge amount of spectrum that will open up for you, and you can ask questions which are very much relevant in today's scenario, even from the research perspective as well. So what I do is, the basic bottom line of the process of it is something like this, that you label the nodes like this, okay, and then you track that who are these people who are connected to one. Okay, so I track that who are the people who are connected to one. So I see in the matrix 2 and 4 are connected to 1. Okay, so if now it's a small network, so you can track it from the network itself, but when it becomes a big network with 10,000 nodes, it will be hard for you to track down from the network picture, but it's very easy to track it down from the adjacency matrix. So you track it that how many people are connected to this particular node and who are those people. That is the more important point in the network approach, right? Then you learn, you use those beta and gamma, those parameters that we had. So beta was the infection probability kind of a thing there, right? So if you remember SIR model, just open up your notebook where you wrote down the equations for SIR model. There you will see that from S to I there was a transition rate of beta. So let us consider that beta to be kind of like the probability of some person getting infected. So say suppose I have beta is equal to 0.5. So we can consider that half, there is a probability of half, that if a person comes in contact with an infected person, they will get sick. Now I have 2 people, right here, 2 people who are in contact with I. So I will toss a coin and decide that who out of these 2 people are going to get sick. Okay, so I will do a random probabilistic event and I will consider that I will toss a coin and I will decide, I will call a random number, so to say, in the language of programming. If you want to hear it, it will be, you call a random number and you see that which of these 2 people, or maybe 10 people or 10,000 people who are connected to this node, depending on how big and how complex and how tightly connected your network is, you decide who are the people who are going to get infected, and in the next time step you make them infected. Okay, and you repeat the step once again. So this is how we study epidemics on networks. This is how you make a realistic study, because there is no probability as such that if one is infected then 5 is going to get infected as well, right? Because 1 and 5 are quite far apart. There is a difference of 2 connections between them, and if one is infected, in the next time step 5 getting infected, the probability is quite low, right? So that we should consider, and this becomes a really important effect when you consider a large network. Not in these small networks, but in large networks this becomes really important, that who is connected to whom, right? So this is how you go on and simulate the network dynamics. So this is kind of a simulation where the similar thing is going on. SIR model, it starts with a fraction of people, like one person among all these network, the entire network sick, and then step by step we use this probabilistic approach to simulate that who are going to get sick. What about recovery? So after a certain amount of time they recover on their own. Okay, so because recovery there also, if you remember, it was not dependent on your neighbors. You used to recover on your own in SIR as well. So in SIR differential equation model also, you saw that people get recovered after a certain time with a certain probability, right? Gamma was the probability. So here also with that probability some people get recovered, some people stay sick for some long time and they recover after that particular amount of time. So if you are interested in simulating this kind of simulation, if you want to see this on your own, you want to tune this beta and gamma and see that how it goes, Network X is a very nicely designed package for you in Python. So if you have expertise in Python, you can go ahead and see how to program these things. If you are not that much inclined to learn Python for this task, you can also dive and see Ion package in Python, which has been a newly written package, which is Epidemic on Network package, and it has been tailored. It has been tailored to designed in such a way that it becomes easier for you to simulate large networks with different conditions that you want. So if you are interested, you are inclined in programming, I request you to go and have a look in these two tools that you have. Ion is basically using Network X, but it has designed it in a better way so that it becomes much more user friendly and becomes easier for you to handle it on networks. So how does the picture change? Is there any change that I have to consider in terms of the SIR model in deterministic and the SIR model in network? If I consider, is there any equivalence between them? So the equivalence is something like this. As you can see, even in the previous example, as you can see that people, you have seen some hubs there, right? These are the hubs who have very much highly connected with many members of the network, and these are the people who are not connected that much. So that means if someone, some hub gets sick, the disease spreads very fast. If this person gets sick, say the person lying at the end of one end of this network, like this person, if he gets sick, the disease will not spread that fast, right? This will be very, very slowly spreading throughout the network. On the other hand, here in the simulation, you see we start the infection from a hub, and immediately in the next time step, several people are sick, right? So that perspective should be included in the consideration of parameters. So equivalence, if I talk about that, how do this beta and gamma of your SIR model correspond to the beta and gamma that I should expect or I should consider for a network model, it should be something like this. This is kind of appropriate choice where you consider that every node has a different power to spread the disease, and then that depends on their individuality, that means their degree. Okay, so the degree of each of these nodes basically control that how much powerful a particular node is in terms of spreading the disease. So this is kind of the equivalence between the SIR model in terms of deterministic equations and in terms of the simulations that we are doing on networks. So this is kind of a picture with 5,000 nodes. This is a simulation where you can see that green nodes are susceptible. red nodes are infected and gray nodes are recovered, and all the light blue lines are basically edges. So this is a simulation that I was performing to demonstrate the SIR model on random networks. Okay, so I will show you these simulations in a couple of minutes. So this is how it will look like when the population, when in steady state, when the disease has spread and nothing much is changing in the picture anymore. In the next step, maybe gradually people will start recovering and so on. So this is kind of a picture of an epidemic, you can say, where a huge fraction of people are infected. Okay, huge fraction of red dots you can see, and still some green people remaining. But this is kind of a steady state where you have achieved. The epidemic has successfully, the virus has successfully spread throughout the population. Okay. So here I must mention that there are other ways to visualize these things as well, which is becoming very popular in this COVID scenario, and while learning about, while trying to understand this epidemic. And this is much more computationally light kind of a tool that we have, and that is lattice. So let me just quickly say that what this lattice model means. So here what you consider is, and this is also could be a very interesting task for students inclined in computation. So what you consider here, you consider a box, okay, and it's a toy population for you. Consider a box, say here I have considered a 400 cross 400 box, okay, a square, and there you consider that it's a community of people, and you randomly fill up some boxes with blue dots like this. So if I just enlarge this portion and show you, this is something that you will see there. Okay, so what is this? Here you have filled up some boxes with blue, some boxes you have colored with blue, and some boxes you kept black, that is empty, right? So every small box or patch here that is blue signifies it has been occupied by a person or maybe a house. So you can consider this to be a locality, seeing from top like a satellite model, right? If you just take a satellite picture of our locality, it will look something like this. So consider this to be something like that. Okay, so every house in this locality is reflected by these dots. So if the dots are connected like this, you can consider this to be a house. These are their neighbors and so on. And roads going on, maybe ponds are in between and something like that. So this could be reflected as a toy population of a toy model, where you can just translate your knowledge of a locality or a town or maybe a country in whichever way you want to make it. Okay. So it's about representation. You can call each of the boxes a person. You can call each of the boxes a house. You can call each of the boxes a locality. Whichever way you want to look at it, you can do that. So this is another way of visualizing it, because here you have a very nice definition of the neighborhood as well. So if you consider that, suppose this is the blue box we are talking about, okay, and this first layer around it could be called the first neighborhood of this person, right? So the immediate neighbors of this person. You can consider this entire 8 neighborhood. You can also consider 4 neighborhood. It's up to you, depending on the kind of simulation you are performing. You can consider it to be a 4 neighbor, like these are the nearest neighbors. You can consider that, or you can consider all the 8 people around them equally probable, equally close to this central blue box. Okay, so this is the d equal to 1 neighbors, because this is the center and this is just one step away from this particular center. Okay, so these are the 1 neighbors of them. These are the second neighbors, second level neighbors. So you can call d equal to 2 neighbors, d is equal to 3 neighbors, d is equal to 4 neighbors, and so on. So if this person or people from this house in this picture, if they are quarantined or if they are not moving much, they are just meeting their neighbors, then you can consider that they just interact and they can spread the disease just around their first nearest neighbor, if the people have restricted their motion very much, right? If they are not moving that much and they are just moving around in their neighborhood only, you can consider that only these people in their neighborhood are there is a probability that they can catch the disease if this person gets sick now. Okay. Now if this person is moving around in the locality, the entire locality, not only the neighborhood but his entire locality, you can consider that this is d is equal to 2, and these many people are interacting, are in close proximity with these people, and if someone is in these boxes, there is a probability that they can get sick. Now if this person moves around the entire town, you can consider d is equal to 3, if and so on, right? You can consider, you can basically estimate the movement of this person, that he can move around the entire town and he can spread the disease to everyone around them. Okay, so this way you can depict the spatial network kind of a thing, where you have the neighbors there in terms, not in terms of the network connectivity or the degree, but in terms of the neighborhoods. Okay, so this is kind of a spatial contact network. If this person moves, you can go on increasing the d and see that how this person can spread the disease. So what will happen, that how will you simulate it in this particular scenario? We call this cellular automata, by the way. Cellular automata, you can just Google it and have a look on different papers, different simulations, programs are available online. You can go and try to run them. So how do you simulate it with your computer? So what you do is that you consider a neighborhood, right? And you can mark the infected people. That is the first step. You mark the infected people, then you mark their neighborhood. So if you are considering that this person is not moving that much, only d is equal to 1, whatever the logic you are following, so then this is the neighborhood that I have. Okay, so only the nearest neighbor, only the d equal to 1 neighbors can get sick. Then you have a beta, right? You have a disease that is maybe spreading very fast or spreading very slow, whatever it is, you consider a beta value for your simulation depending on what kind of disease you are dealing with, and then you decide that which one out of these neighbors might get sick. Okay, so if the probability is very low, then maybe no one gets sick. If the probability is a little bit higher side, maybe one of the 8 people will get sick. If the probability is very high, then maybe 6 out of 8 people will get sick in the next time step, depending on what is the value of beta, what is the probability. So that probability is basically a given factor, or a factor dependent on the disease itself. So the probability or beta is the how infectious the disease itself is, right? So the disease itself decides that what would be the value of beta, how infectious the disease is, what is this probability going to be, and accordingly the next time step you will have a picture of your toy population where someone else is also sick, and you come back and you repeat the steps again and again to see how it happens. So let me just show you how it should happen. So here I have considered a 400 x 400 toy population, you can say, okay, and I have filled it up with people. The blue dots are all people, and then the disease starts spreading from some random people. So how many people I have kept sick in this entire population? You cannot even see them, right? In this total population, I just have 20 people sick. 20 random spots I have chosen and made them sick, just like this, just like the previous picture. Here I have marked them red. So here also I have marked them as red in this box. You cannot even see them. Now the disease spreads from them. So here I have modeled an SEIQR model. What is this means? Susceptible, then exposed, which is a very closely related to our COVID scenario. Exposed means you have come in contact with, you got exposed to the virus, you come in contact with someone who is sick, right? But you are not even showing the symptoms now. So the green dots here actually signify that you are exposed to this particular virus. Okay, and then in the next step you get infected, you start showing infection symptoms, and you get infected, and then if you are detected, you are detected, then there is a probability that you will be quarantined, and then finally you will recover. Okay, so these are the steps that will happen. So in these two populations you can see that the disease is spreading in completely different speed. Okay, so here the disease is much more restricted, and here the disease is spreading like anywhere and everywhere. Almost every people are sick. Almost all the dots have turned red. That means almost all the people are sick. So what is the difference between these two? Different things can control this. For example, a dense population versus a scattered population. And that is a major problem in India, right? Our population density is really high. So in a dense population compared to a scattered population where the density is low, if you start with a similar city, a toy city or a toy population, and you introduce similar number of sick people in it, and if you see that how the disease spreads, it will be completely different in nature. So here you can see in the dense population the disease is spreading like extremely faster, and in the scattered population on the other hand the disease is not spreading very fast. It's even restricted to a very small percentage of the total people who could get sick. So all the blue dots here are signifying susceptible people who could get sick, and the yellow dots are recovered. So here you see the entire population got sick. So entire population passed through the virus, and that basically signifies that a certain percentage is also suffering from death and also a huge loss in economy as well. So similarly, if you consider pictures where lockdown can be implemented, so you can consider that, or movement restriction you can say, right? So in this way you can simulate different aspects. For example, here in the left one I have simulated a complete lockdown versus lockdown with a certain free period. So suppose in this simulation on the left hand side here we see a complete lockdown. Here when the lockdown is lifted just for one time step, or the movement restriction is waived for whatever reason, it might be consider the election scenario. So if people just stop obeying the rules for a certain period of time, or a very small period of time even, how drastically different results can occur. Let me just show you once again. So here a complete restriction or complete obeying of rules is taking place, and here on the other side you say for a very few days or a very small amount of time people are ignoring the rules, and most of the time they are obeying it, right? But even when it's happening, you can see a sudden jump in the level of infection. Here you can see a sudden jump in the level of infection as soon as it happens. So the green population, you remember, it's the people who got exposed, and gradually people among them start showing symptoms as well, and finally they are either quarantined or they are giving support in the hospitals. So this is how the system evolves, right? So these simulations are really not that difficult. If you are inclined computationally, you can go ahead and perform this. So now let us ask some relevant questions because we learned about networks, we learned about heterogeneity, individuality, and how to implement them on epidemics. So what changes? If I had the differential equation, what particular thing changes? Do I still have an epidemic threshold, say like R that we had, reproduction number, you remember, right? R was defined by beta by gamma in case of your SIR, simple SIR model. For every model you can estimate what would be the reproduction number, and it will estimate that there is a threshold below which the disease cannot spread that much. It will not turn into an epidemic, and above which it goes to the red zone where it becomes more and more the problem becomes more and more, and the number of people who got infected, their fraction also increases, right? So is there still an epidemic threshold if I consider networks? So let us consider random networks first. So random networks, as you remember, everyone has a certain probability to get connected to everyone. The average degree the degree distribution was you remember how it looked, right? So there were no such importance of hubs there. Average degree is more or less something which is fixed. So in a random network, say I run a simulation where my beta by gamma is 0.5, okay, and I start with 70% of infected people in a population. So I start with a population, a random network of 5,000 nodes, and you can see a huge number of red dots here, right? Huge number of red dots here to begin with. I start with a huge number of infected people with R equal to 0.5. That means a disease. So remember that R is dependent on beta by gamma in case of SIR model, right? Beta the infection rate, gamma the recovery rate. So beta by gamma was equal to R. It is a disease. We are talking about, say, a disease where the reproduction number is 0.5. And I start at t is equal to 0. The first time step, there were 70% people who were sick. Now as the simulation goes on, is equal to t is equal to 0, this is t is equal to 50, this is t is equal to 200, this is t is equal to 400 time steps, different time steps. So infected people are spreading the disease and they are recovering as well. Susceptible people are getting sick by the infected people, and the simulation runs one by one time step, it goes on. And what happens is gradually you can see the number of red dots is decreasing and vanished completely. Okay, so that means if your R is less than 1, then even if you start with an initial infected percentage which is quite high, you finally result into a scenario when no one is sick. So the epidemic threshold is kind of holding, right? So let us just go on and see what happens for R greater than 1. So here I have run a simulation for R is equal to 1.66, and here I have started with the same network. With the same network I have started with I initial equal to 2%. So in the total population only 2% of them are sick. Here you can see very small fraction here and there, you can see some red dots sitting, and most of them are susceptible. Green means susceptible, just remember that. Most of them are susceptible, only 2% were sick. Okay, R is equal to 1.66, the simulation runs, t is equal to 1. Within t is equal to 11, you can see quite a high percentage of people getting sick. So sorry, this is t is equal to 40 actually. So in t is equal to 40, you see 30% of people are already sick. Okay, so that means R as an epidemic threshold is working fine for random networks as well, but there is a condition. If the average degree is very low, that means the connectivity is very sparse, your adjacency matrix is very sparse, here and there you have some connections but you do not have a very tight connection, then this behavior that you can map the random network behavior to the differential equation behavior is kind of gets lost as soon as the network becomes sparse. So and this is very much true, because if you consider a differential equation model, you are basically considering that anyone can infect anyone. So a random network where everyone is connected to everyone, that is basically a scenario of deterministic model, right? So here if the random network becomes more and more tightly connected, then the convergence of these results towards the deterministic result, towards the differential equations that you have seen, becomes more and more. It becomes sparser and sparser, the divergence becomes more. Okay, now let us talk about real networks. So by real networks I mean real contact networks. So here there are several websites, you can just go and Google. Nowadays it's very easy, you just Google and see that a network repository, and there are several online network repositories which will give you actual networks of people, how people are connected to each other. These are 3 networks I am showing here: a contact network between jazz musicians, an email network in an university, a connection or friendship network in a particular website where it's a friendship social network kind of a thing. Okay, so each of these networks have some number of nodes. These are all real networks. Remember, all these nodes are actually real people. These connections in email network basically means who mails whom in a particular university. Jazz network, who is friend with whom, right? So here the nodes are all real people, edges are all real friendship or relations or contacts. Average degree, you can just calculate at the average degree of these systems. What is the maximum degree? What is the node that has maximum degree? What is the degree of that particular node? So these are the characteristics of these networks you can study. And the main thing that you see in these networks is that they are not very similar looking with the random network that I have. As the number of edges become more and more, as the connection becomes more and more, they get closer to the behavior of random networks, but they are not looking like the random networks that we have just discussed, right? So what happens if I simulate the disease or the rules that I have just told you, the way we simulate it, if I simulate it on these particular real networks? So in case of random network, whatever we are seeing, that is different from what we see in scale-free networks or real networks, okay, because of presence of these hubs. I am sure that you remembered that in scale-free networks we talked about that there is a fraction of nodes, a very a small fraction of nodes in case of this scale-free networks. There is a very small fraction of nodes who have a very high number of links, right? And those nodes we called hubs. Their existence is very prominent in case of scale-free networks and also in real networks, while very small number of links in the people where the number of links are small, their number is quite high. Okay, in real networks, this is very true. And the threshold condition, very interestingly, does not hold, and that's a very important observation when you turn in from a random network to a scale-free network. That means in a scale-free network, due to presence of hubs, drastically different results could be observed, where the epidemic threshold is absent. Even for a very small fraction of people getting infected, scale-free networks are capable of spreading the disease to everyone, turning into an epidemic because of presence of hubs, these high degree nodes. And these high degree nodes and hubs are very important in our society as well, in our contact networks as well. So if you look around us, this is the main reason that we are not living in the world of homogeneous mixing or the random networks. The networks are very well designed. If you want to say, if you just try to estimate their properties, you will see they have a very prominent presence of hubs, people who meet thousands of people in a day, and most of the people do not meet more than 10 or 20 people in a day, right? So this drastic difference, this presence of hubs makes this problem very interesting, where in these real networks there is basically no epidemic threshold, no story of R equal to 1 is there. So disease will spread if you start with a very small fraction as well. Okay, so in this way you can basically go ahead and explore different perspectives of a disease or different kind of spreads. For example, you can make the network itself dynamic. That means that it can happen. So each and every point I will discuss one by one. So static network means the network is fixed. The network is fixed, but the disease is propagating. So if you go on and look into this model, in these particular all these particular figures, the network that I considered, the adjacency matrix that I consider was fixed. Okay, it was not changing. The connections between people, the friendship between people are not changing. On the other hand, you can make this network dynamic. That means where there is an avoidance between people. So as the disease spreads, it can happen that the people are stopping to meet other people. The network connection or the adjacency matrix itself evolves. So here you can say that the adjacency matrix evolves with time. Along with the network, the adjacency matrix also evolves with time. You can consider small and large networks, and you see that how different results you can see in small networks. Okay, clustering. We have talked about clustering, where you have some small tightly connected groups and some loose connections among these groups, which constitutes the entire network. You can consider that kind of a network and simulate what is happening there. And correlation between disease propagation, weighted networks, where all the connections are not of equal weight. Some connections are very strong, some connections are quite weak. You can consider that kind of a scenario as well. So this way you can make your networks different, and you can simulate different kind of epidemic spread on these networks. Moreover, beyond epidemic, you can also think about different other things that can spread on networks. For example, what else can spread other than a bacteria or a virus, right? An idea can. For example, an opinion about a global issue can spread from friend to friend. A habit can, like smoking, bad habits, that can spread from person to person. Information spreads. Information about some new technology or some mobile app, it spreads from person to person. Scientific theory, for example, machine learning, it has become a boost, it has shown a revolution in last few years, and it propagated from person to person. Okay, rumors, sensitive issue rumors, they spread very fast through our social network. Trends like online shopping, it was not there even like 10 years back, right, anywhere, but now everyone shops everything online. So this way, marketing and political campaigns, obviously they spread over person to person in social networks. So this way many different things can spread in the same way, like the simulation technique that I have just taught you. So I request you to dig deeper and think about these different kinds of problems that I just exposed you to, like network rewiring, how network changes, clustered networks, groups and families present. Study immunity. That is also an interesting aspect, that you consider that some people have taken vaccine, or some people have a very rigid opinion about they don't think that COVID is much serious and they will always go out. So difference in opinion. Okay, so some people who are not going to change their opinion, some people who are not going to get sick ever, something like that you can consider. Okay, yeah, and you can also consider competition with delay, which is a very interesting fact, that now vaccination is there in our country. People are taking vaccine, and here you can also see that a huge peer influence is there. So people usually at the first step, when they heard about the vaccine, they were a little bit skeptic, but as soon as they hear that someone in their family, some relative or some friend have taken the vaccine and they are well, they are becoming interested to take the vaccine. This is a very, very common thing. So you can see that on one side in the same network, the disease is propagating, right, and it is propagating in form of a virus, where you have your own logic that beta by gamma, and this way the disease is propagating, and with a delay, maybe after some time, the vaccination dilemma is also propagating, and that is like an opinion, just as I just said, that is like also a peer influence, right? Here also people get influenced by their friends or their family members that they will take vaccine or not, and these two dynamics are coupled with each other, right? So you can basically address these research level problems if you just learn how to simulate networks. So those who are interested, I will ask you to dig deeper, and you are free to contact me if you want to proceed in this line. Okay, so here we conclude our discussion on module 3, biological networks. We are done with it. Here I am concluding it. I will send this study material to you for your study. So study about it, ask me questions if you have any in the coming classes. So a little bit of exposure to image processing in coming to 2 classes, though it's a very vast subject. I'm sure it's a very vast subject, and it is I cannot do justice to image processing in 2 classes, but still I am sure that it will at least give you some flavor of it, and you will be able to take up from there and proceed if you want to have or address a problem in future related to that. So let me stop here for today. If you have any questions or queries, please go ahead and ask me in the coming classes. See you in the class. Bye.